Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video we are going to continue a series I've started earlier in some other videos where we look at exterior calculus and how to express electromagnetism within this exterior calculus formalism. And there are plenty of things that kind of come much more easily in this particular case. And what we are going to see today is basically that we actually get two Maxwell's equations essentially for free out of the formalism. Okay, so that's what we are going to see today. Okay, so as usual, when I discuss things related to exterior calculus, because this is not something that is often kind of known by people interested in physics, or in fact in applied mathematics or theoretical physics, then I feel kind of obliged to always do some sort of recap. I will put some link to a video somewhere where we discussed these basics of exterior calculus, but basically there are plenty of videos where we basically have added stuff as we went. Okay, so just kind of bear with me, try to follow. If you can't follow, maybe you want to go back to some other videos related to exterior calculus. But basically the point here is that we take a space here. We are going to say this is Rn. We can view that as a manifold, but I've not talked necessarily about manifold at the moment, so let's just look at Rn here. And the whole point of exterior calculus concerns the exterior derivative, okay? Because if we want to do a sort of calculus, we need to have a notion of differentiation. And so here, we actually differentiate things that are called form. And the way I prefer or I like to introduce these things is basically as follows. So you look first at the notion of zero form. And a zero form is nothing but a scalar field. So what it is basically a function that takes in a kind of entry x1 to xn, so basically n variables, and then returns a number. Okay, so that's a scalar field, that's a so-called zero form, and then we, by definition, say that the exterior derivative of such thing is going to be what we call usually the total differential of the function. And so that's simply the sum of the partial derivative with respect to the respective variable xi, and then times dxi. Now that's the whole thing about exterior calculus, is basically that these dxi's are going to appear about everywhere. And here, because we've got dxi there, we actually call that a one form. And the degree of the form is related to, in fact, the number of times you're going to see these guys being made product with each other. Okay? Now, it turns out that this is what I explained here. If you've got what is called a K form, then this is basically, so K, by the way, has to be less than or equal to n, the actual number of dimensions in your system. And then this omega is going to be the sum. The sum here has to be ordered in that way, or at least ordered in some way, so that basically you don't double count things. And here, this omega I1 to Ik, these are simply indices, and you need to have k indices in each omega here. And any of these guys is basically a sort of component of the K form omega with respect to this sort of basis. So that's, you can view that as a sort of basis vector, and where this thing here is called the wedge product. And the wedge product is really a simple product, if you will, that formally speaking, the only thing we care about at that stage is that omega wedge, omega prime, where omega and omega prime are a priori different forms, then this is going to be equal to minus omega prime wedge omega. Okay? Now, consequently, what happens is that if you take any K form, omega, and you wedge with itself, then you're going to get zero, strictly zero. okay? Because that's the only thing that can be basically itself and minus itself. So that's the idea. So once you have a K form like this, then you can look at what the exterior derivative is going to look like. And again, the simplest way personally I like to introduce here is basically say that this is simply, I repeat the expression here, and I simply put d omega, and then wedge, and then the rest of it, okay? And the omega, again, remember the d omega of I1 to ik is basically a component. And there are many of these components, of course. But the bottom line is that these omega, these components as themselves can be seen basically as zero forms. And so I'm applying the definition here of d omega on the zero form in that fashion. And then I just need to apply the definition of the wedge product, and I'm going to get a result. And that's the kind of things we're going to explore in this particular video anyway. So that's kind of the bottom line of the basis of the vector calculus, of the exterior calculus, sorry. Now, one of the things we had seen in previous videos is that if we look at electromagnetism in R cross R3, so R here corresponds to the time variable, then we actually have one more dxi that can appear instead of the standard dx, dy, dz. We can have dt coming in. And so we introduced what was a one form, which was the so-called the vector potential one form. And this is basically minus v dt and then plus ax dx plus ay dy plus sz dz. Now, we dedicated a whole video to show that if we look at the we define the electromagnetic form, or two form, as f being equal to dA, then we managed actually to split it in that particular format. So it was E wedge dt, where E is to be interpreted as the electric field one form, and then B here is a magnetic field two form, okay? And in fact, here E is expressed in that fashion, and B is expressed in that particular fashion, okay? So again, I will put a link to this particular video if you want to have some idea about what we did and how we got there. Now, what we do in this video is to realize that there is a property, and I'm not sure you can see it here because I know there is some reflection there, but it's a property we've derived some time ago in one of the videos on exterior calculus, whereby we showed, or at least we showed in a simple case and accepted its generalization, that if we apply twice the exterior derivative onto any form, okay, k equals, well, basically here I say k less than n minus 1, but in principle it's actually even more trivial if k is equal to n, for example, because then it's going to be trivially 0, because you're going to have, let's say, at least, let's say, a dt with any other dt, or a dx with any other dx that is already there, etc. So it's going to be trivial. But the bottom line is that you've got whatever the degree k you've got, then applying twice the exterior derivative gives 0. Consequently, for us, we actually get that d to a must be equal to 0. Okay? And what I want to do here is basically, that's really a very, very simple property. We had applied that property before to basically to show that we had some other properties coming in. In fact, that was to talk about the gauge freedom aspect. But here, this is something slightly different. We apply d squared onto a itself. Okay? Now, this has to be 0, so what that means, obviously, is that df is equal to 0. That's equivalent, by the way. Okay? And let's see what that means, and whether we actually get something that we recognize if we have some knowledge of electromagnetism. So, df equals 0, this is going to tell me the following. So, this is telling me that, so df let's work out what df is already. So df is equal to dE wedge dt, and then plus dB. Okay? Now, let's try to work out what dE actually is. So dE is equal to dEx wedge dx plus dEy wedge dy plus dEz wedge dz. Okay, so here are multiple things to realize. At the end of the day, what we want is to actually put this expression dE inside there, okay? So when I'm actually going to, so Ex, Ey, and Ez are zero forms. They are kind of scalar functions of x, y, z, and t. Now, what that means is that when I apply the total differential here, I should get partial derivatives and the corresponding kind of d things that should be, there should be a dt, a dx, a dy, a dz. Now, in this particular context, when I calculate dE, I need to be aware that basically is going to be wedged with dt. So what that means is that, yes, if I calculate just dE, I need to have in principle a component that is going to have some dt there, but I know that when I'm plugging it back there, I'm actually going to get a dt wedge dt, which is 0. Okay? So the bottom line here is that I'm going to keep only the terms that are going to matter when I plug it back in there. Okay? So what I'm going to write here is not dE per se, it's actually the dE that I need to put inside this expression, and that is going to be non-zero. Okay? Likewise, here you've got a wedge dx. So what that means is that I can't take the dx part of the total differential because dx wedge dx is 0. And of course, dy wedge dy is 0, and dz wedge dz is 0 as well. Okay, so keep these things in mind because that makes obviously the calculation faster because we have less terms that we have to take into account. So the equal sign I'm writing here is not an exact equal sign, it's an equal sign with respect to the terms that are relevant to the calculation I want to do here. Okay, so keep this in mind. And so then what we are going to get is the following. So dEx dy dx plus dEx dz dz wedge dx. And then plus d. So here, this is simply the first term here. Now we do the ey, so plus d ey dx dx wedge dy plus dy dz dz wedge dy, and then plus dez dx dx wedge dz plus dez dy dy wedge dz. Okay? Now, remember that dy wedge dx is equal to minus dx wedge dy, and then, and vice versa. So we can take any of these products and swap them and put a minus sign. And this allows to make some form of factorization, and that's what I'm going to do here. So we are going to get, for example, here, dx wedge dy, and that factorizes, so let me find dx dy, so that's dey dx minus dx dy. Now, dx dy, let's see, let's say, for example, dz wedge dx. That's going to be, let's find a dz dx. So here we've got dx dz, and then minus dz dx. And then the last one has to do with dy dz. And then that's, let's find one, dy dz here, so that's dz dy minus dy dz. Okay, so basically we've got now an expression for dE. So that's one thing done. Right, so now let's have a look at B. Okay, so B is like so. And because, so here I need to be a bit careful. Because I've got, because you've got here only you've got a two form, there is only one spatial coordinate that can work. So for example, when I'm going to take the differential of bx, I'm going to get dbx dx dx plus dbx dy dy plus dbx dz dz plus dbx dt dt. And the only spatial part that is going to work is the x part, the dx part, because if I have dy or dz, it's going to essentially return a zero. Yeah. Okay. So that's exactly the same strategy as before. If I calculate dB, so let's try to work this out. So dB is going to be dbx and then dy dz plus dby dz dx. Sorry, wedge dy, and here likewise, I need to put the wedges here. I need to put correctly the wedges. So here I've got wedge dy dz. Okay. Here I've got plus d by wedge dz dx, and then plus dbz, and then wedge dx dy. Okay, so that's what we've got to calculate. So again, that's a very similar logic to here, except that I have even less spatial coordinates that are going to matter. But now I need to not forget the time component. So what I'm going to get is the following. I'm going to get dbx dx, and then dx, that's it. So maybe I can put it, I'm just thinking here about how do I do, but yeah, so here I'm going to get dbx and then dx dy dz. Then here I'm going to get dby dy, and here what I'm going to do is that I'm going to get dy dz dx, and what I'm going to do here is basically I'm just trying to see, yes, what I'm going to do here is basically perform swaps between the dx, dz, and the dy that I'm going to get from there to directly get the same volume element here, dx, dy, dz, so-called volume form. It's just because otherwise it's going to take a bit too long. And if you've got any question about this part, I'm happy to actually show you again how that works. Likewise, here I'm going to get dbz, and then dz, and then again dx, dy, dz. And again, you need to swap things around, and each time you swap, you get a minus sign. And for all of these guys, it turns out you need to swap twice. And so you get minus times minus, and that's a plus. Okay, so here, that's what you've got. And then we need to have the time component. So that's dbx dt. And then that's actually dt wedge dy dz, and then plus dby dt, and that's dt wedge dy dz. No, that's dz dx, sorry, dz dx, and then plus dbz dt, and that's dt wedge, and that's dx dy. Okay, so it looks kind of complicated. I will have to erase on that part, so you can always anyway kind of go back in the video and check what these terms were. So I'm erasing here and we'll continue on that side. Okay, so I've erased and I've rewritten dB in a shorter and more compact version. So dB here, you may recognize, if you factorize by dx, dy, dz, you may recognize the actual form the divergence of some vector b. So here I'm going to say that b is equal to a collection of functions, that bx, by, and bz, and basically that corresponds to a specific kind of orthonormal basis, etc. But that's kind of the idea. So it's a collection of fields, if you will, or components of a specific form, for example. And so here I'm just saying that this is a divergence of that particular field time dv, where dv is the volume form, that is dx, dy, dz. Okay? Now, what I've done as well, again, to make things a bit clearer and a bit easier to use once we put everything into df, is basically I've actually realized, I mean, not realized, but I've used the fact that if you take dt here, you want to put it in the same form as what we are going to get here. You want to get the dt on the rightmost part of these forms here. So what you need to do is basically drag the dt from the first to the second position, and then from the second to the third. So essentially, as you do so, you basically get a minus sign each time you do that. And for every one of these guys, you need to do it twice. So therefore, you get a plus sign. So that's what basically I've used here. Now, what we can do is basically put all of that together. And I'm going then to factorize things. So we are going to get the divergence of b, and then times this dv, which is this form here, and then plus, and let's try to look at what we get. So we are going to get, for example, here, dbx dt, and then let's see what else we have from let's see, yes, let's see what else we have. So here we've got this, and so now we need to compare with what we have from here. Okay, so we need to have the part that is in dy dz. So dy dz here is this one. So we are going to get plus, and here this is dez dy minus dey dz, and so all of that is actually in front of dy dz, if I'm not mistaken. That's dy wedge dz, and then wedge dt. Okay, so then we continue. We are going to get here, let's put it this way. So we've got dz dx, and we are going here to get dby dt, and then plus, and then this here is going to be, let's retrieve it, so that's again dz dx. dz dx is dex dz minus dz dx, sorry, let's write this properly. Okay, and finally we are going to get dbz dt. Let's think here, and that's going to be dx wedge dy, and then dt, and that's plus. And so we need to look for the dx dy, that is here as dey dx minus dx dy. Okay? Now, what is interesting is that now when you apply the formula we wrote just here, df equals 0, what that means is that this quantity has to be 0. But this is a form, that's a so-called volume form. This is another 3 form, but that's not the same as this one. That's another 3 form, but that's not the same as this other 2. And that's another form that is not the same as any of the other 3. And the bottom line is that they essentially work as basis vectors. of basically this df. And because they are basis vectors, they are linearly independent, and therefore what must be true if this is equal to 0 is that the prefactors of these vectors have all to be 0. Okay? That's the definition of linear independence in linear algebra. And so what we get out of this is the following quantity, or the following two equations. In fact, if we write them in vector equation, is divergence of B is equal to 0. And then what we get is the following. We get that the time derivative, the partial at least time derivative of B plus, and here I'm going to introduce the curl. Usually that's going to be written that way. That's not necessary. Is equal to 0. And just to make sure here that what I've introduced is that the vector, where did I put the B before? Yeah. And so here I've introduced a vector E, which is basically, again, simply containing like a list of the components, like fields. And then again, this is to be understood as being in the actual thing. And then I interpreted this particular component here as components of the curl. Okay. And so that's how you can do that. One way to see that, by the way, is as follows. Let's take another color. This one works. So one way to actually look at this is to realize that you can use a Hodge dual. I'm going to put a link to a video where I discuss this, but the dy wedge dz is actually the wedge dual of dx. And then this, for example, here is a wedge dual of dy, and here is a wedge dual of dz. And by the way, I'm talking about the wedge dual here in, so I need to specify what I mean. This is in 3D, and this is in the case of Euclidean metric in 3D. Okay, so that's what I mean by the Hodge dual in this particular context. And so what you see is that this term here is essentially the x component of a cross product. Okay, so that's how you can recognize that this is a curl. But basically here, these are two Maxwell's equations, right? So, so these things are two Maxwell's equations. And the only thing that has made us actually take some time is simply the interpretation of a specific equation that takes 2 seconds to write, but a bit more time to interpret in a language we're used to in, let's say, traditional textbooks or undergrad textbooks here. Now, this in exterior calculus, as we have said earlier, actually reads simply df equals 0, okay? Which is incredibly simple to remember and to write, okay? So basically that's df equals 0. So we've got 2 out of the 4 usual Maxwell's equations. Now it takes a bit more work, or at least more background, in order to get to the other 2 Maxwell's equations. So that's something we'll do in a different video. If you've got any questions or comments about this particular video, by all means do let me know in the comment section, and otherwise see you in the next video.